So in this video we are going to discuss the question in thermal and statistical physics which appeared in JRF physics science examination that occurred in December 2012. Okay, so let's continue with the first question. The statement is the free energy difference between superconducting and normal states of a material is given by the expression which is delta F, that is equal to Fs minus Fn, and that is equal to A psi square, it's not A but it's alpha, and then beta by 2 psi 4. Okay, where it's given that psi is an order parameter and alpha beta are constants such that alpha is greater than 0 in the normal and alpha is less than 0 in the superconducting state, while beta is greater than 0 always. The minimum value of delta F. Okay, so here for the system to be stable, we will follow the rule of energy minimization. So that means when this the free energy to be minimum, so that means the differential delta F with respect to order parameter which is psi, okay, that should vanish basically. Okay, so that means this implies this is equal to 2 alpha psi plus we will have, when while differentiating with respect to psi, we will have 4 beta by 2, so that is equal to 2 beta and then psi cube, and that will be equal to, that should be equal to 0. So here we can rewrite this as psi into 2 alpha plus 2 beta and then psi square. Okay, so here either the psi is going to be equal to 0 or this expression will be equal to 0, but as we have argued that it is for instance when we talk about the this ferromagnetic system, so this phase is stable at high temperature. Okay, whereas for the for the superconducting state, okay, in the superconducting states we cannot take this value to be equal to 0 in principle. Okay, so that means we have to equate the expression inside the bracket that to be equal to 0, and if we do that, we obtained psi mod square that is equal to minus alpha by beta. Okay, so now the minimum value of the free energy that's given by substituting the value of psi square in equation 1. So put this value in equation 1 and we obtain the minimum free energy, that is delta F, that is equal to alpha into psi square, okay, which is minus alpha upon beta its square. Okay, sorry, no, not this is psi square. Okay, and then plus beta by 2 then psi square ka square. Okay, so that means minus alpha by beta and its square. So this is equal to minus alpha square upon beta, and then this will be alpha square upon beta square, or what you can say alpha square upon 2 beta. Okay, and in principle you can say that this is equal to minus alpha square upon 2 beta. Okay, so minus alpha square upon 2 beta, so therefore option B is the correct one here. Let's continue with next problem. The statement is a given quantity of gas is taken from state A to C reversibly by 2 different paths. Okay, so we are given a process which can occur by 2 different paths. Okay, either from A to C directly or from A to C via point B. Okay, and it's shown in this figure here. So during the process A to C, so let's try to find out the unknown things in process A to C. So when we are following the path AC directly, the work done by the gas is, so we are given that dW, that is equal to 100 joule. Because it's work done by the gas, we are taking it as positive. Okay, so and the heat absorbed, so it's given that during this process dq, that is equal to 150 joule. Okay, now from this these two values, what we can do is we can find the internal energy change during the process when we are moving from point A to C. Okay, so for this purpose we will make use of the first law of thermodynamics, which is du, that is equal to dq minus dw. So that's the first law of thermodynamics. Okay, so internal energy change between point A and C, so let me write it as AC, du AC, du AC, that is equal to dq, which is 150 joule. Okay, minus what is dw, this is 100 joule. So this internal energy change is equal to 50 joule. Okay, now let's see what is given during the process B to C, A to B to C. Now while following the path A to B to C, okay, what is given to us? The work done by the gas is, now again the work done by the gas, that is equal to 30 joule. The heat absorbed is how much? So we have to find out that what is the dq equal to when for this process A to B to C. Okay, now if you just take a look at these two different paths, let me call this as path 1 and this as path 2. So while moving through path 1 or path 2, initial and final equilibrium states, they are identical. So when initial and final equilibrium states are identical, so in that situation the internal energy change between those two equilibrium state is going to be identical. It doesn't matter whether you follow path 1 or path 2. So that means du AC, that's going to be same here also, which is 50 joule. Okay, so we can easily determine dq by making use of equation 1, which is the first law of thermodynamics. So dq for this process will be equal to du AC plus dw, and that is equal to du AC is 50 joule and dw is equal to 30 joule. So that means the heat exchange involved during process A to B to C is 80 joule. Okay, so that is our answer. So therefore option B is correct here. So let's continue with the next problem. The statement is, consider a system of 3 spins S1, S2 and S3, each of which can take values +1 and -1. The energy of the system is given by the expression, which is E equal to -J into S1, S2 plus S2, S3 plus S3, S1. So let's call this as equation 1, and where J is a positive constant, so it's given to be a positive constant. Okay, the minimum energy and corresponding number of spin configurations. So we have to determine the minimum energy and the corresponding spin configuration for this particular system. So here, because it's given that each spin Si, it can take a value of +1 or -1. Okay, so we will look for the possible configuration, and from there we are going to determine the minimum energy for out of those feasible configurations, and the corresponding number of spin configuration for which the energy is minimum. Okay, so because here we are given a spin system of 3 spins. Okay, number of spins are, they are 3. Okay, because each spin has 2 possibilities, either it can have a value of +1 or -1. The total number of spin configuration, that is equal to 2 power number of spins, which is 3, so that is equal to 8. So let's try to work out what are those possible spin configurations. So here I'm going to list all those configurations. Okay, so I will assign a value of +1 or -1 to each spin, S1, S2 and S3. So we are going to make a table, and with the help of a table then we will work out the possible energy values also, S1, S2 and S3 okay, where the energy EI is determined by using equation 1. Okay, so let's first list the various possibilities of the spins. Okay, so the if we okay, so here we will make an assumption that we will assign for the spin up, we will say that it's equivalent to +1, and when the spin is down, so this is equal to a value of -1. Okay, so here up, up, and up, and then another possibility could be down, all spins are down. Okay, and remaining 6 options will be up, down, and up. The next possibility is first is up and remaining 2 are in the downward direction. Okay, and then first 2 pointing in the upward direction and the third one in the downward direction. Okay, and next possibility could be down, up, down, down, up, up, down, down, and up. Okay, so let's try to evaluate the interaction energy for the first case. I mean for this one. Okay, so E1, let's call the interaction energy as E1. So that is given by equation 1. So minus J outside S1 S2. So here S1 and S2 both they are pointing in the upward direction. So here I will write 1 multiplied by 1 plus S2 into S3, S2 into S3 both pointing in the upward direction. So this is 1 multiplied by 1 plus S3 into S1. S3 is also pointing in the upward direction, S1 is also pointing in the upward direction. So 1 into 1. So the interaction energy is minus 3J. Now similarly for the second configuration, so that means this one, let the interaction energy is E2. So minus J outside, and then because all these 3 spins they are pointing in the downward direction, so here we will have minus 1 multiplied by minus 1 plus minus 1 multiply by minus 1 and then plus minus 1 multiply by minus 1. So this will give us so this minus 1 and minus 1 multiplication, that will give us plus 1. So ultimately this is equal to minus 3J again. Okay, now similarly for the one can easily verify, so let me write the corresponding energy here. This is minus 3J and this is also minus 3J when both all 3 spins they are pointing either in the upward direction or downward direction. And for the remaining configuration, one can easily verify that the corresponding energies are J, 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 and J. So this way we are having only 8 possibilities, 1, 2, 3, 4, 5, 6, and these 2 possibilities with minimum energy of minus 3J. So therefore from this exercise we notice that the minimum energy is equal to minus 3J and corresponding number of configuration are number of configurations with minimum energy, they are equal to 2. So therefore C is the correct option here. Let's continue with the next problem. The statement is the entropy S of a system is related to the accessible phase space volume gamma by the relationship S is equal to KB ln gamma, which is a function of parameter n, e, and v. Okay, where e, n, and v they are the energy, number of particles, and volume respectively. From this one can conclude that gamma, so we have to identify the correct option. Okay, so here we conclude that in equilibrium gamma is going to be maximum. Okay, and the reason is that because in equilibrium the system stays in the most probable macro state. The system stays in most probable macro state, and the most probable macro state is the one having largest number of microstate. Okay, so that means when the system it exists in equilibrium, so that means definitely it's going to be in the most probable microstate having largest number of microstates. So that means the corresponding value of the gamma in that case, that's going to be maximum, and that will maximize the entropy also. So therefore in equilibrium not only the gamma is maximum, but entropy is also be maximum. So therefore option C is the correct one here. Okay, let's continue with the next problem. Here we are given that delta W with the work done in a quasi-static reversible thermodynamic process. So delta W, that's the work done in a quasi-static reversible process. Which of the following statement about delta W is correct? Okay, so delta W is a perfect differential if the process is isothermal, and delta W is a always perfect differential. Delta W is a perfect differential if the process is adiabatic. Okay, so let's see in principle work done, it's a path dependent quantity, and this answer we can this question we can answer by making use of the first law of thermodynamics, which says that du that is equal to dq minus dw. Okay, so when the process is adiabatic, in an adiabatic process we have dq that is equal to 0, so which implies du is equal to dw. But as we know that the internal energy change, it is a perfect differential. So that means it is a path independent quantity. So therefore in an adiabatic process the work done also become a path independent. Okay, path independent. So therefore in adiabatic process the work done becomes a perfect differential. So it's a yes, so that means B is the correct option here. B is correct here. Let's take a look at the next problem. So consider a one-dimensional Ising model with n spins at very low temperature. Okay, when almost all spins are aligned parallel to each other. Okay, so there will be a few spin flips with each flip costing an energy of 2J. Okay, in a configuration with R spin flip, the energy of the system is given by this expression. Okay, and the number of configuration is given as NCR, where R varies from 0 to n. The partition function is okay. So we can generalize this result by simply starting our discussion from the n is equal to 1 spin. Okay, so when we say that there is only one single spin, so the R, the possible value that R can take, it's either 0, that's there is no spin flip, or there is 1 when there is a flip. Okay, so R is equal to 0 corresponds to no flip and when there is a spin flip. Okay, now the corresponding partition function is given by Z1, that is equal to summation R is equal to 0 to 1 and exponential minus beta E1. Okay, now where E is given by the expression that is given to us, E that is equal to minus Nj plus 2 Rj. So here what we are going to do is, because we are taking n is equal to 1 here, and we will assign the value to R from 0 to 1, because we are only taking one single spin. Okay, so therefore the partition function for this situation will be R taking value from 0 to 1 and then exponential minus beta and then minus j, because n is equal to 1 here, plus 2r j. Okay, so this is equal to, so we will have only two terms here, so exponential minus beta minus j plus 2 into 0 into j. Okay, and then the second term corresponding to one spin flip, exponential minus beta into minus j, and when r is equal to 1 plus 2 j. Okay, and that comes out to be equal to exponential beta j plus exponential minus beta j, and that's nothing but this is equal to 2 times cos hyperbolic beta j. Okay, so now what will be the situation for the two spins? Okay, so from here we can immediately write the expression for the n spin system Zn. Okay, so that is equal to 2 cos hyperbolic beta j power n, Z1 power n. Okay, or this is equal to 2 power n multiply by cos hyperbolic beta j power n. If you just compare the options that are given to us, then the most appropriate option here, it is D here, but here we are having an additional factor of 2 power n here. Okay, so I have seen over the internet a few people have given the solution for this problem, and they are talking about the division by a factor of 2 power n, but I mean, there's no justification, a proper justification that is given to the division by a factor of 2 power n here. Even if we just take an example of two spins further. Okay, of course the answer here, it's most appropriate answer here, it's the option D here. I agree with that. Okay, but I do not agree with the fact that this is the correct one, and the reason is that suppose we are having n is equal to 2 spins. Okay, so there will be in total there will be 2 power n, that is equal to 4 microstates. Okay, and these microstates are given as when both of these two spins, they are aligning either in the upward direction or downward direction, and the other two categories are up down and down up. Okay, so the point is that when because here suppose this is the initial situation. Okay, and either there's going to be no spin flip. Okay, when there is no spin flip, then we will have a this situation. Let's say this is initial situation. Okay, and when there is one spin flip, so when there is a one spin flip, either the left spin can flip or the right spin can flip, and accordingly we will obtain these two situations here. Okay, and when both of the spins, so here this situation corresponds to r is equal to 2, and these correspond to r is equal to 1 and r is equal to 1, and this corresponds to r is equal to 0, which is the number of spin flip here. In principle, both of these two configurations, they are identical. Okay, they're not different basically. Okay, and these also, you can say that these are identical. So we should, in principle, we should count only two configuration here. Okay, so that means while considering two spins here, so we should make a division by a factor of 2, not by a factor of 2 power n. Division by 2 power n mean we are going to for the configuration of for the system of two spins, we need to divide by a factor of 4, which is ridiculous in my opinion. Okay, so in my opinion there should be a factor of 2 power n should be attached here, and that's then that will make it the correct answer. Let's take a look at the next problem. This problem is from Bose-Einstein condensation. The statement is, non-interacting bosons undergo Bose-Einstein condensation when trapped in a three-dimensional isotopic simple harmonic potential. For Bose-Einstein condensation to occur, the chemical potential must be equal to, okay, so let's pay attention to the line that I have highlighted here. It's a three-dimensional isotopic simple harmonic potential. Okay, so this potential can be represented as VR, that is equal to m omega square by 2 into x square plus y square plus z square. It's isotopic basically. Okay, so the ground state energy for the bosons for this case, okay, the energy eigenvalues for the one dimensional potential, because when we talk about a one dimensional potential, so this is n plus half h cut omega naught, you can say, okay, or h cut omega, whatever you call it, okay. So n can take value from 0, 1, 2 and so on. So when we are having isotopic three-dimensional potential, so here we will have three different indices for n, n1, n2 and n3, and that will be equal to n1 plus n2 plus n3 and then plus 3 times 1 by 2, so that is 3 by 2 and then h cut omega, where n1, n2 and n3 they can take value from 0 and so on, okay. So for the ground state energy, let me call that E0, that corresponds to n1 equal to n2 equal to n3 and that is equal to 0. E0 will be 3 by 2 h cut omega, okay. So let me call this as equation 1 and this as our result 2, okay. So now we have to look for the condition for the Bose-Einstein condensation to occur, and the condition that the chemical potential must satisfy, okay. So if we recall what we have learned while going through the Bose-Einstein condensation, so for temperature much smaller than the critical temperature, all atoms will be in lowest energy state whose occupancy is given by the bosonic distribution function, okay. So which is equal to the occupancy of the ground state, that is equal to n naught, and this is equal to e power E0, that's the energy of the ground state, minus mu upon kT minus 1, okay. Now for temperatures, so let's call this as result equation 3, okay. Now for temperature much smaller than critical temperature, okay. So that means for temperature that approaches toward absolute zero, it's not 0 Kelvin but approaching 0 Kelvin, n naught should be very large, okay. For temperature smaller than critical much smaller than critical temperature, and n naught should be very large, n naught should be very large. And if you just take a look at equation 3, when n naught will be going to be a very large number when this exponential is close to unity, and when the exponential will be unity when E naught minus mu upon kVt, this is almost equal to 0, or when this is very small, you can say is very small, close to 0 but very small, okay. And when this is very small, so we can approximate the exponential term here in equation 3, exponential E0 minus mu upon kT, this can be approximated as 1 plus E0 minus mu upon kT plus higher terms which we are neglecting here, okay. So now make use of this result in equation 3. So n naught will be 1 upon 1 plus E naught minus mu upon kT plus so on minus 1. So 1 and minus 1 will cancel with each other, and this is equal to kT upon E naught minus mu, okay. So now when t is equal to 0, when t is equal to 0, this implies mu is equal to E naught, okay. Whereas when t it's not equal to 0, so that is for non-zero temperature, mu should be mu should be smaller than E0. Okay, so this is basically the condition that that need to be satisfied so that we can have a non-zero or excessively large occupancy in the ground state. Okay, so therefore the necessary and sufficient condition for the Bose-Einstein condensation to take place is that when we are having a mu which is less than or equal to 3/2 h cut omega naught, which is nothing but this is the ground state energy E naught. Okay, so therefore the C is the correct option here.